So what's the goal today? By the end of this class, you're going to know what a critical number is. So there are critical numbers and there are critical points. We'll make a distinction between those two. I'm going to be able to use the first derivative test to check the nature of the associated critical point. All right, so there's something called a first derivative test. I want to learn what that is. All right, so what is a critical number? Critical number is any value that could create a local min or local max. We know what local mins and maxes are. So any value of x that could lead to one of those things, a max or a min, we're going to call it a critical number. That's the value of x. So we say that x is equal to c is a critical number if the first derivative, that's what f prime c means, is equal to 0. We say that f of c is a critical point. So here's a distinction now, that the x is just the x value of the coordinate of a critical point. And a critical point has both an x and a y. Okay? So once you get the value of c, the value of x, which makes your derivative, your first derivative equal to 0, then you can find the value of y to see what your critical point is, meaning what is your x, what is your y. You're going to put that value of x, which is the c in this case, back into the original function to get your y value. We're going to call it a critical point. So we can find critical numbers by simply setting the f of x equal to 0. And we've been doing this. This is not something which is completely shocking or completely new to you. When you were being asked to find maxes and mins before, you were doing that. You were setting the first derivative equal to 0, because you look at that and see that means there's a horizontal tangent. It probably means that we have a max or a min. So these numbers, three things are likely to be happening. They have a local max, a local min, or something called a saddle point, and we'll talk about what that is in a minute. So we're going to test the nature of these critical points by using this first derivative test. Okay. First derivative test. You assume that the f prime of c is equal to 0. Therefore, there's a critical number when x is equal to c. If the f of x changes, and I talked about this on Friday, you hopefully remember this. If the sign of the first derivative changes from negative to positive at the x equals c, so before c it was negative, then after c is positive, then it means that you have a local minimum point. And I want you to think about it this way. It's very simple to remember this. I wouldn't memorize this. I would just sort of think about it this way. It had a negative slope followed by a positive slope. It means I'm coming down and then I'm going back up. So I must have a minimum point there. Think about the slope of a line that is approaching a minimum point. It's negative because it's going down. And then after that point where it's a minimum, it starts having a positive slope. And that would mean that you have a local minimum. If f of x changes from positive to negative at x equals c, then f of x must have a local maximum at that point. So you started off being positive, then you went negative. So it means that you probably have a local maximum there at that point. If it doesn't change at x equals c, then you may have what's called a saddle point. And let me just talk about that a little bit right now. Consider that you have a cubic function, right? A cubic function can look something like this. So let me try to put that in a different color here. I'm not going to use the eraser anymore. I'm done with the eraser. But you know, you've seen cubic functions that look something like that. Well, that's neither, there is going to be a point somewhere in the middle here which has a horizontal tangent. Somewhere there is a horizontal tangent. But it does not result in a max or a min. What's happening is that it looks like it's about to, it goes from a positive, goes to a horizontal tangent, and then it goes back to a positive slope again. So this is what we're saying could happen, and it causes what is called a saddle. It looks kind of like a saddle on a horse kind of thing. I guess that's why they call it a saddle point. So that's why I use an example of y equals x cubed, because it looks like it's about to turn into a maximum, and then it sort of does this thing and keeps going up, and it's not a maximum at all. So call those saddle points. So local min, negative slope followed by positive slope. Local max, positive slope followed by negative slope. The easiest way to do this is create a first derivative table, meaning look at the slope just before the critical point, look at the slope just after the critical point, and compare those two slopes. Did I go from positive to negative, or did I go from negative to positive, or did I just stay negative, or did I just stay positive? That's what we're talking about. Okay, let's find all the critical points and establish their natures for this example. All right. So very simple to find that first derivative, right? We're experts at this now. That would be equal to x to the power of 4 minus x cubed. Let's see, that would be minus 2x squared, and then the 9 will disappear. Okay, so, okay, I'm thinking, remember we need to figure out where this thing is equal to 0. That's where critical numbers are. And the first thing I'm noticing on this thing is that this has a common factor of x. So I'm going to factor out that common factor. That's equal to x into x. Actually, x squared is a common factor. I just noticed that x squared is a common factor. So that's equal to x squared minus x minus 2. Okay. And that can be further factored. Right? X squared is a common factor. That can be further factored into x minus 2, x plus 1. Okay? So, what are my CNs? Remember, my critical numbers are the things that make this equal to 0. So, critical numbers are what I'm looking for here. Can anybody give me what those critical numbers are, please? Right? Give me all the critical numbers that would result from setting this thing equal to 0. That's how we get our critical numbers. Help me out here. Okay, Ashvan is first out of the gate. Thank you, Ashvan. 0, 2, and minus 1. Thank you, Sarah. Taj agrees as well. So 0, these are my numbers, not my critical points. 0, 2, and minus 1. Okay, so here's what we're going to do. We talked about setting up a table. We've seen interval tables before, or you have anyway, or should have by now. So let's start off at putting these in order at minus infinity up to minus 1, starting at the lowest number. Then I'm going to go from minus 1 to 0. Then I'm going to go from 0 to 2. Then I'm going to go from 2 to infinity. All right, so I'm just running the gamut here. I'm starting at minus 1, going to my lowest critical number, which is minus 1. Sorry, minus infinity. Taking my lowest critical number, which is minus 1. Then I go from that critical number to the next lowest critical number, which is 0. From 0 to 2, from 2 to infinity. Sorry, that last one isn't right. I'm getting so scared of using the eraser. So I'm just going to put a little thing here to make that into infinity. All right, so that's infinity. You have to entrust me on that. That's infinity. All right, so I'm going to choose a number in each of these intervals, like let's say minus 2. And we'll say, I guess the only thing I can put in here that's reasonable is minus 1/2. And then I'm going to go with 1. I'm going to go with 3. So as long as that number is inside of that interval, then I should be good to go, right? Something that's pretty close to either side of that interval is what I'm doing here. Okay, so let's put the minus 2 in. And all I'm interested in knowing is what's happening as I am approaching that critical number, that x value, what's happening at the function. So I'm not going to choose a test number that's far away from minus infinity to minus. I'm going to choose something that's pretty close. So I'm looking at the the minus 2. And I'm thinking, if I put minus 2, what we're trying to do here is just put it into the derivative and see what's happening at the derivative at that point is really what we're trying to do here. Okay, so putting minus 2 into this is, and I'll just use, I'm reluctant to do this, but I'm going to use, I actually have to use eraser here. So I'm just going to put the minus 2 into this. So this part's going to be positive. This part is going to be negative. And this part is going to be, let's see, negative as well. All right. So all I'm doing is I'm just plugging in the minus 2 into each of those different factors and asking the question, what's the derivative doing at that point? Well, what do you think, folks? If I have a positive and 2 negatives, and you're thinking it's going to be positive, good. Okay, so positive there. That's my short form for positive, by the way, a plus sign with a VE after it. I'm going to do the same thing again. And by the way I do it is I just simply count the number of negatives the number of negatives is odd, then I know the result is negative. The number of negatives is even, then I know that it's likely to be, if it's even, to be positive. Okay, so I'm going to erase this stuff here. Let me do this actually. All right. I'm going to go back and hope that this thing is going to work. So x squared, x, okay. So I'm putting in minus a half now. This is, of course, still going to be positive. It's always going to be positive. Then minus a half here is going to be negative. And minus a half here is going to be positive. So I'm thinking, and we can always draw this afterwards, by the way. So I'm thinking, again, I said count the number of negatives. And if I'm counting the number of negatives here, there's only one negative, which would mean what to you? If I count the number of negatives. Sarah was first out of the gate the last time. What does everybody else think? I have one negative, so negative. Okay, so let's put that in. Let's just keep going here. I'm going to erase these again. And I'm going to put in the 1 now. 1 should be easy. This is always positive, right, because I'm squaring it. And this is negative now. And this is positive here. So what does that suggest to you? Are we talking positive or negative here? We're talking negative. And then we're putting in the 3. So let me erase this again. I should probably not erase the x squared because I know that's always going to be positive, but anyway. So I'm thinking this is going to be positive again, has to be. This is positive, and this is also positive. And of course, that is pretty obviously going to be positive there. If everything is positive, it's going to be positive. So the question we ask now is, as I go, you know, in between at this minus 1 here, right? I went from positive to negative. What does going from positive, based on what we've been saying today, if I'm going from positive to negative, what does it suggest about that minus 1 critical number that we talked about? Let me fix this back here. This is minus 1. What does that suggest about that that number going from positive to negative? That there's a local max there, Tash says. And everybody buy into that. Does that make sense to everybody else? Tash is thinking a maximum. Actually, okay, good. So this is suggesting a max here. As I go from the 0, what's going on at the 0 in your mind? I went from being negative to being negative again. What does that suggest to you at the 0? Because that's where the bridge is. What's going on there? Right? It was negative and then it stayed being negative. What is it? What is it saying to you there? The saddle point. Okay. I just use abbreviations there. And then from the one that's going negative to positive, what is that suggesting to you? So it starts out being negative, then becomes positive. What's happening at 2? Right? What's going on at 2 minimum? Okay. And you can always check that for yourself with a graph, right? But we're saying that this graph has a local max, has a saddle point, so a local max at minus 1, saddle point at 0, and some kind of a minimum, local minimum at 2. That's where those two things are. That's the bridge. So on either side of this, and always, again, take points that are pretty close to the number that you're trying to investigate. So I'm choosing 1 on one side and 3 on the other. All right. Okay, so that was pretty easy, hopefully. Let's now talk about this. But wait, there's more. Kind of like when you're selling stuff on television. Turns out that we can have a critical number when f of x is not equal to 0, such as when we have a cusp. Now, we've talked about cusps before. It's like when you have the graph having a little point in it. So it comes down and it sort of collapses on itself. This is what I call a cusp. These tend to occur with cube root functions when you have like like when, okay, I'll give you an example. If you have a function like x to the power of 2 over 3, if you were to graph something like that, that would actually have a cusp in it. And what's happening is that you're taking a cube root and then you're squaring it, and it looks something like that. That's really what that means, by the way. So a regular cube root function does not look like that, but it's still, and in fact, a regular cubic function, just so you know, it does have what's called a vertical tangent. I'm going to try and draw one, which I'm not going to do a good job at it. When you have some time on a Desmos graph, I don't want to switch over to a Desmos graph now. Try to graph x to the power of 1/3, right? And you're going to find that it has what's called a vertical tangent in it, right? So it's not differentiable where that vertical tangent is. We talked about the fact that some functions are not differentiable at certain points. And one of them is when you have like a cusp like this, and the other one is when you have a vertical tangent, so it's not differentiable at that point. But it does have minimum value. You can clearly see that this function, even though you would say that this function, the f of x at that function, because you can't differentiate at that function, is not equal to 0, you still have a critical number. So here's what we're saying. Yes, we can. A local max or min occurred without y prime being equal to 0. Therefore, we have to extend our rule that critical numbers exist either when you have y prime being equal to 0 or when y prime does not exist. So if when you are trying to solve it, if when you have a derivative, right, and there's some value which makes that derivative undefined, then that could also be a critical number. So that's just an FYI, right? So when you're dividing by something or you take, anything of that nature, then you could have a critical number there, but you're saying it just is because you can't define the function at that particular value of x, all right? So that's another way that we can have a critical number, either when it's equal to 0, the derivative is equal to 0, or when the derivative does not exist at a particular value of x. You could still have a critical number there. Okay, let's keep going. So find all critical points and establish their nature. So this one is kind of what I was just talking about a while ago, right? I'm gonna draw that for you in a minute, but it is really, if you look back at the previous page, this is x to the 2/3, where you take a cube root and then you square it. That's really what this is, right? I'm taking x minus 4 and I'm raising it to the power of 2 and then I'm cube rooting it. Or whether you want to cube root it first and then raise it to the power of 2. But I mean, it doesn't really matter because the exponent on this is still 2/3. So what I'm going to do is I'm going to show you first of all what this graph looks like. You can clearly see that there's a cusp on this one, and the cusp occurs right here. So having said that, let's do this mathematically now. Let's see if we can figure out what the critical points are. Remember, critical points are not the same as critical numbers, but they're related. A critical point is an x and a y coordinate. And then we're going to figure out what the nature is. Now we have the answer because we have the picture already. But let's see if we can figure this out using the derivatives. Okay, so first things first, let's take this x. Let me go back to black here. I'm hoping this thing is not going to flake out on me today. X minus 4 to the power. I'm going to make this to the power of 2/3 because that's the same thing. All right. Raising it to the power of 2 or 3 is the same thing as squaring it and then cube rooting it, or cube rooting it first and then squaring it. It doesn't matter. All it doesn't matter. The fact is that it still represents an exponent of 2/3. So what we're going to do now is we're going to go ahead and find the derivative. So dy dx is equal to 2/3 x minus 4 to the power of, now if I have 2/3 and I take 1 from that, I'm left with minus 1/3. Okay, you can confirm that with a little simple math. So this is equal to 2/3 times the cube root of x minus, oh, by the way, this is multiplied by the derivative of the inside, which is simply 1. So I guess I should have said that. This is really the chain rule in action here. So 2/3 of this, x minus 4 to the minus 1/3, times the derivative of x minus 4, which is just simply 1. So that's why I didn't say it, but that's really what we should have interpreted from that. So 2/3, the cube root of x minus 4. Okay. So, and hopefully this format for the derivative makes sense to everybody. Right, what I've done is I've left a 2 on top, and I put the 3 as a denominator. This is not 3 to the power of 3. In fact, let me make sure it's obviously not 3 to the power of 3, so I'm going to erase this here. and make it a little bit more obvious, and say 3 times the cube root of x minus 4. Okay? So the question now becomes, this is my dy dx. Is there a value that makes this thing become 0? That's the question we're asking. Right? Can you think of any value of x that will make this become 0? Can I set this equal to 0 and solve it? Is that possible at all? Right? What do you think, folks? Can I solve that? Set that equal to 0. Is there a solution for that? 2, Tamalea thinks. So you're thinking if I put 2 into that, I'm going to get 0. All right, we can try that out and see what happens. So you're saying the cube root of 2, 2 minus 4 is minus 2. So you can find the cube root of that. That's true. But is that 0 though? That's the question. Is that equal to 0? What do you think, Tamalea? Is that going to give me 0? Remember, the only way to get 0, I'm going to remind you of this now, from a quotient is from the numerator. That's the only place to get 0 on a quotient. And this is a quotient. All right? Do you see what I'm saying, Tamalea? I just want to make sure you're clear on that. If I have a quotient, x over, numerator, denominator, right? The only place to get that whole quotient to be 0 is if the numerator is 0. Right? It's like cross multiplying at this point. If I cross multiply right now, so the bottom of this side times the 0 is going to be what's left. So you're going to be saying that 2 is equal to 0 is really what you're going to have, which is of course not true. So the only place to get 0 is the numerator. And that numerator is a constant. So guess what? This does not have any value of x, which makes this equal to 0. Does that mean there are no critical numbers? Well, we just learned that's not the case. If we can find a value of x that makes this function undefined, that would be a critical number. Okay? So, what value of x makes this undefined? That's the question we have to ask. Right? What number, what value of x can I put into this function, this dy dx right now, that makes this undefined? You can't solve it when you set it equal to 0. There's nothing there. But is there a value of x that makes this undefined? Well, can I get that from the class? Can anybody give me an answer to that? Is there any number that makes this become undefined? I'm not getting anything from anybody. Nobody can think of any number that makes this undefined. How do you figure that out, Tar says? It looks like it might be 4 on the graph, but not sure. Okay, well, let's think about this. If I have a rational function, when is it usually undefined? What value of x usually makes it undefined? What value in the denominator, I should say, usually makes it undefined? 0. Okay. Can I make that denominator become 0? Yeah, thank you, Fernando, and thank you, Stephen. Okay. So if I can find a value of x that makes that denominator become 0, that's going to be the number that I'm looking for. And in this case, that number is 4, because when x is 4, you write that down. When x equals 4, dy dx is undefined. Right? And what that means is that 4 is a Cn. It is a critical number. Okay? So, what we have to do now, and by the way, it's a critical number. Let me just tell you why. Because it's undefined. It does not exist. The dy dx does not exist when x is equal to 4. Right? So 4 is a critical number. It says find all the critical points. So what we need to do now is to take that 4. Point means I need the x and the y. I need to take that 4 now and put that 4 back into the original equation. The original equation is up here. Y is equal to the cube root of x minus 4 squared. So I'm going to go ahead and put that in my function to get my critical, the y value. So y, what do we know what the critical number is equal to the cube root of 4 minus 4 squared. All right, let me take you back and show you the function again. It's cube root x minus 4 squared. So I'm putting in my 4 as my critical number, 4 minus 4 squared, and that's very clearly equal to 0. So here's my CP now. My CP is 4, 0. My critical point is 4. My critical number, let me say that again. My critical number is 4. Putting 4 into the original equation gives us 0, very clearly gives us 0. So my critical point, which is now my x and my y, is 4, 0. All right, that's my critical point. So the next question is, now we can see clearly from the graph that it is a minimum point. That's hopefully pretty obvious. But what we should now do is to put the number that we have, 4, just before 4, so maybe 3, and after 4, which is 5, into this and see what kind of answer we're getting. Okay? So we're now trying to get the second part of the question. First part of the question is find out critical points. There's just one. 4, 0. That's the critical point. What kind of critical point is it? Well, here's our derivative right here. Let me circle that for you. Right? There's our derivative right there. We're going to put a number just before 4 and after 4 and see what the result of that is. So here we go. So dy dx at x equal, let's just use a table. We used a table the last time. So we're going to go from minus infinity to remember it's at 4, so we're going to go to 3 to 4, sorry. And then we're going to go from, actually we only need 2, 4 to infinity. Yeah, we just need 2. We don't need the rest of the table. I'm just going to erase that. Since there's only 1 point, we just need that. So I'm going to choose 3. I'm going to choose 5. All right, those are the two numbers I'm going to work with, dy dx at those 2 points. And I'm going to remind you what dy dx is. It's 2 over 3 times the cube root of x minus 4. All right, that's what we're playing with here. That's the number that we're putting in. So if I put 3 into this, I'm going to get 3 minus 4. Oh, by the way, we need to know whether it's positive or negative. I'm going to get 3 minus 4, which is minus 1. By the way, can I take a cube root of minus 1? Is that even possible? Does minus 1 have a cube root? Or am I off on the deep end here? What's going on? Does minus 1 have a cube root? Can I take the cube root of minus 1? Yeah, it is minus 1. Thank you, Sarah. Right? And thank you, Stephen. It is minus 1. So that's actually fine. And then 2 over that is going to give me a positive number. Sorry, it's going to give me a negative number. All right, so I have a minus coming out of this, and that's going to make, so you have a top that's positive and a bottom that's going to become negative. So that's going to be a negative answer. If we put 5 into this, then clearly we're going to get 5 minus 4, which is 1. Cube root of that is positive. This whole thing becomes positive. So you look at that and you're thinking you're negative and then you become positive. We talked about this before. A negative followed by a positive, that must mean that we have a what? A max or a min. Forget the graph for a minute. Right? I know we've seen the graph and maybe I shouldn't have shown you the graph at the beginning. Is that a max or a min? Don't look at the graph, just think through. Started off negative, went positive, it is a min. There you go. So there's a min at 4, 0. Okay, clearly we saw that from the picture, right? So the critical point, the 4, 0, is a minimum point, right? Now, we got into trouble trying to set it equal to 0. That didn't work, but we still found out that we can have a critical number even when you can't get a 0 from the derivative. As long as you can find one where it doesn't exist, you can use that as a critical number. All right? Okay. Let's move this thing along. I'm anxious for us to get back to the stuff on the... I'm not going to draw this one first. We're going to actually see if we can come up with an answer for this. I'm going to, as I said, I want us to go back to the stuff that we did on the University of Waterloo website, but we're just going to continue with this. So this one is a cube root of 2x plus 5 multiplied by minus 3x squared, and it's a product. So I think we know that we have to use a product law on this one. All right. So hopefully everybody remembers the product law, and we'll draw it afterwards. We'll get the smartboard to draw it for us afterwards. So we take the derivative of the first part of this, which is the minus 6x, and multiply it by, I need some space, so let me see if I can get this out of the way here. So the derivative of the first part of this, which is the minus 6x, times the cube root of 2x plus 5. I'm still not getting a lot of space here. All right, let me move this out of the way a little bit more. You can bring that back in later on. Actually, you know what? I'm going to take this and make it into an exponent. So let's just change this up a bit here. I'm going to rewrite this as minus 3x squared times 2x plus 5 to the 1 over 3. All right, just to make things easier for all of us. So, excuse me. So dy dx is equal to the first part of this, which is the minus 6x, not squared anymore, right? The 2 times the minus 3 minus 6, times the underived second part, so 2x plus 5 to the 1/3, plus the underived second part, which is actually, I can put that as a minus. That probably makes sense. So minus 3x squared times the root of the second part, which would be 1 over 3 times 2x plus 5, and then 1/3 minus 1 would give me minus 2/3. Okay, I hope everybody is following me so far. No, we have some tidying up, and oh, times 2x. Sorry, times 2. Forgot that part, times 2, because I have to take the root of the inside. Let's just double check this. And, you know, I'm always willing to take correction from you if I make a mistake when I'm doing anything. And most times you're quite good at that. So let me go back and make sure that we did this right. The root of the first part, so that's the minus 6x, times underived second part, so 2x plus 5 to the 1/3. And then we're going to take the second part underived, which is minus 3x squared, times the root of the second part, so that's 1/3, 2x plus 5 to the minus 2/3 times 2. So let's see if we can tidy this up just a little bit. So that would be minus 6x times 2x plus 5 to the 1/3. And this would be, let's see now, that these two cancel each other out. So I'm going to have minus 2x squared. And let's put that over the cube root of 2x plus 5 all squared. I'm hoping that makes sense to everybody. Right? Are we good to go with that, first of all, before I go any further? Does that all make sense? In fact, for this one, I'm gonna keep the exponent as it was. I'm gonna put the exponent back as being, let me just change this up here a little bit. And there's a reason that I'm doing that. So let's put this as two x plus 5 to the power of 2/3. All right. Okay, so the minus 2x squared goes on top. I'm just going to make sure I did that right. So that's the 3 times the 3. That cancels out. And that's the 2 times the 2x. Okay, right. All right, so let me just do a quick check-in here. Excuse me. Carly, how about you? And let's see, Kashaf. Carly and Kashaf, how about both of you? Is Carly there with us? Where's Carly? And Kashaf, how about you? Okay, good. All right. So I know one of the things that sometimes people have a difficulty with is trying to come up with like a common denominator when you have two fractions like this. Can anybody suggest what might be a good common denominator so that we can put this over 1 if you like, so that we can combine these two into 1? Can anybody suggest what might be a good common denominator for this? All right, so one denominator is 2x plus 5 to the 2 over 3, and the other denominator just seems to be 1. Is there a common denominator? So 2x plus 5 to the 2/3, Ariana says. Let's try that. This might actually not be a bad idea. So 2x plus 5 to the 2/3. Excuse me. All right, so you see what Ariana put there? She's using the denominator of the one on the right as the common denominator. So let's just think this through now. What do I multiply this by that gives me this denominator down here? Well, it'll be 2x plus 5 to the 2/3, which if I multiply that by the top, that means that I am adding those two things that have the same base together. Let me make sure everybody follows that, right? This 2x plus 5 to the 1/3. Okay, let's do it this way. What am I multiplying this by? Let me point to it. What am I multiplying this by that gives me this denominator here? Well, it'll be 2x plus 5 to the 2/3. So let's multiply that by the top. When I multiply that by the top, the 2x plus 5 times the 2x plus 5 to the 1/3 times the 2x plus 5 to the 2/3 means I'm adding those exponents together, right? Which would give me just simply 2x plus 5. I hope that made sense to everybody. To the power of 1 then, which is just the same thing. And then minus 2x squared. Now let me pause because I want to make sure everybody followed what I just did. Did that all make sense? Minus 6x, minus 6x. Oh, yes, yes. Thank you. Thank you very much. Yes, yes, for sure, for sure. For sure. Right, I think I just figured out when this board crashes when I use the eraser. So when I use the mouse to point to the eraser, that things go haywire. So as long as I use the cursor to get the eraser, I think I should be okay. But thank you, Sarah. Thank you very much for causing me not to embarrass myself on that one. But is everybody following this? Let me say it one more time, just so everybody is okay with it. We took the advice that we got from Ariana by using the denominator as being the 2x plus 5 to the 2/3. All right, so now we have to ask, what do I multiply this? Let me point to it. What do I multiply this denominator by of 1 to get this denominator here? The answer, of course, is 2x plus 5 to the 2/3. So I have to multiply the top of this fraction by that. So 2x plus 5 to the 1/3 times 2x plus 5 to the 2/3. Same base, add the exponents. 1/3 plus 2/3 is 3/3 or 1. So this just becomes 2x plus 5 to the 1. And then we still have the minus 6x there. And then, of course, would I multiply this denominator by to get this? It's just simply 1. So it's 1 times the top, which is minus 2x squared. Okay? All right. So I want to make sure everybody's okay with that. We're going to move along now. Let's tidy up the top. So that would be minus 12x squared. It's a good thing that Carly caught that. And then minus 30x. And then minus 2x squared. Right? So minus 12x squared minus 30x minus 2x squared. Okay. So, and then this is all over the same denominator of 2x plus 5 to the 2/3. Okay. And then on top, I'm going to get, what is that? Minus 14x squared minus 30x. And then all of that, of course, is over 2x plus 5 to the 2/3. And I can obviously factor out minus, what is that, 2x, leaving me with 7x plus 15, I think. Minus 14 minus 30, yeah, okay. Over 2x plus 5 to the 2/3. If I'm going too fast, I'm quite happy to stop and talk about this some more. Okay. So where does that lead us now? It leads us to the point where we're trying to figure out critical numbers. And that, of course, means setting this thing to equal to 0 and solving it, but also asking, is there a value of x for which this does not exist? Because that could also be a critical number, right? Is there some value of x that causes this thing? And remember that this thing at the bottom here is a cube root. So maybe I should write that as a cube root now that we've dealt with it as an exponent. So let's see now. Minus 2x, 7x plus 15 over the cube root of 2x plus 5 raised to the power of 2. Okay? Okay, let's see now. Why does the number say I can't? What does the numerator say? Oh, can you read? Oh, you say you can read it now in the bracket? In the bracket. So the cube root of 2x plus 5 to the power. Okay, you say you're okay now. Okay, you got it. All right. Okay, so let me go back and look at the question again. Oh, let me go back and look at the question again and see what we're being asked so we don't go off on a tangent here. Find all critical points and establish their natures. Okay, critical points. So we need critical numbers first, right? What are the CNs in this case? Critical numbers that you can see from here. So critical numbers would come from either when you could get it to be equal to 0, or you can get it to be not existent, something that makes it not exist. So can anybody think of some numbers that we can put here as critical numbers? Give me some critical numbers, please. It's 2:19, so I'm trying to see if in the next 15 minutes we can get to the stuff that we have on the University of Waterloo. Any critical numbers that you can see here, people? Anyone at all? Come on, want to get that from the class. I don't want to have to give everything to you. What critical numbers can you see here? So minus 2.5. Okay. I agree, by the way. What are the critical numbers? And 0. Good. Anything else? Any other critical numbers that you can see here? Because there is one more. Okay, there's one that I'm not getting from the class. And you know what? Sarah and Carly and people like those have been rock stars. I mean, really sort of stepping up. But I don't hear enough from everybody else. So minus 15 over 7. Thank you, Richard. So let me go back and look at the question again and establish their natures. This is a lot of work, but you know, we tell you what, let's have a quick look at the graph just to make sure that we hopefully are on the right track here. So we're saying that these are all critical numbers at this point. Minus 2.5, 0, minus 15 over 7. Let's see what the smartboard thinks about that. Whoa, all kinds of stuff going on here. Now, unfortunately, this doesn't have all the cool features of Desmos where you can click on a thing and see what's going on, you know, sort of like the way you would on a Desmos chart. But having said that, you can probably see that this minus 2.5 that we talked about is here, right? Somewhere around here. And the graph stops, by the way. There is a limit to this graph. You notice that it just sort of reaches a point and then just doesn't do anything. And then there is this other point here, which looks like it might be the minus 15 over 7 that we talked about before, that we got from Richard. And then there's a 0 over here, which we also talked about. Now, clearly, we can see that it would seem that this down here is like a min, and this looks like it would be a max over here. And this one just kind of runs out of steam. It just does nothing. So it's really neither a min nor a max, right? But it is kind of still a critical number because the graph just kind of runs out of steam right there. So the graph is actually undefined on one side and probably has a slope that's, you know, that we can look at on the other. Okay, so let's see if we can quickly establish, we'll just tell you what we'll do, right? In the interest of time, because I would like us to be able to get to the stuff that, let me see what's on the thing after this. Okay, I would like us to get to a few of those questions on the University of Waterloo website, but let's just see if maybe we can look at one of these points and see if it makes sense with the derivative that we have. Let's take the 0, because 0 is a nice, easy one to work with. Let's see what's happening at 0. So here's our derivative right here, right? So 2x, like I said, all this stuff here is our derivative. So we're going to take a point, actually 0, we're not actually going to use 0. We're going to use probably -1 and 1. That's probably what we're going to use here. So let's put -1 into this function and see what happens, all right? So putting so what if I could copy this onto another page? Let's do that. This is our derivative that we came up with. And let's open up another page here and just paste that in. Okay, so that's our derivative that we came up with. And let's check out the -1 and the +1. So on either side of the 0, right? That's what we're trying to do. All right, we know what the graph suggests about that point. So here's our point 0. I'm going to take out the -1, put in a -1, put in a +1, and see what the derivative is telling us, that first derivative. So putting -1 into that would give us -2 times -1, 7 times -1, plus 15 all over the cube root of 2 times -1 plus 5, and all of this squared. Well, we know the bottom is going to be positive for sure, right? Because it's squared. So we're not going to spend a lot of time on that. There's a point at which the bottom is definitely going to be squared. So we know it's going to be positive. And on top, though, we're going to have a positive here being multiplied by, this is going to be positive as well, right? So as you can see, -2 times -1 is positive. This -7 plus 15 is going to be a positive. So positive, positive is going to be positive on top. So positive on top, positive on top. So it means that in just before the 0, we have a positive slope. So positive slope at -1. Let's do the same thing now at -1. So the same thing, I'm going to copy it again. So here's our derivative again. But now we're putting in +1 into this. So that's equal to -2 times +1, 7 times +1 plus 15. And I'm not, again, going to concern myself with the denominator, because the denominator we know is positive. Hopefully everybody accepts that. So this part is positive here. This part is negative. So that means that this is going to be a negative. So the slope, just to be consistent, the slope is negative. So negative slope at x equals 1. So if we start off with a positive slope, end up with a negative slope, then we know that 0 is a max point, which it actually does appear to be. Right? If you go back and look at the graph again, 0 does look like it's a max point. And if we did that same thing for the this -15/7, then I'm sure we'll get that being a minimum, and this one is going to be inconclusive.